Hello everyone. This video is part of MSBD 5012 course in machine learning. Today we are going to present our project, Cardiovascular Disease Prediction. In this presentation, we start off by talking about the background and the dataset. Then we move on to data exploration, feature selection, the models we use. Finally, we talk about the result and continue with discussion later on. Introduction. According to World Health Organization, in 2017, cardiovascular disease, or what we call CVD, is the leading cause of death globally. The ability to predict accurately whether patients are having CVD or not can be a real game changer to the medical industry. Machine learning techniques have been increasingly used to aid the clinical analysis. With this in mind, our group made an effort in order to contribute to the good cause by doing this project. And in this project, we compare different machine learning models, which are logistic regression, naive Bayes, decision tree, random forest, and deep neural network. We use the results and discuss their performances. Data exploring. Our dataset is a medical data containing 11 input features and one target variable. The features are age, height, weight, gender, systolic and diastolic blood pressure, cholesterol, glucose, smoking, alcohol intake, physical activity, and our target variable is presence or absence of CVDs. There are three features: objective features, examination features, and subjective features. Objective feature is the factual information of the patients. Examination features is the data from the clinical examination. Subjective features are the data obtained directly by inquiring the patients. Some features are numerical, some features are categorical, but our target variable is binary. These are the plots that we generate to see the distribution of values of numerical features. These are age, height, and weight. We can see from these graphs that three features show the normal distribution. We also plot the correlation matrix, which is a square matrix that shows the correlations between each variables. The score ranges from 0 to 1, where 0 shows no correlation and 1 shows high correlation. The scores of some of the important correlations are shown in this table. Feature selecting. There are three feature selection methods that we use in this project. The first is called select-k-best. Select-k-best uses chi-square test, which is a statistical test designed to test the significant relationship between two variables. The features are then ranked by chi-square score for each feature. The next feature selection method is lasso cross-validation. Lasso makes a linear model and selects the features by shrinking some coefficients and set the other coefficients to 0, and finally returns the good features. The final selection method is recursive feature elimination, or RFE. RFE is a feature selection method that fits the model and removes the unimportant features in every time that it trains models until the specified number of features is reached. Features are then ranked by the importance.
In our project, we compare the prediction accuracy of 5 different models. The first model used is logistic regression. As the target variable we are attempting to predict is dichotomous, denoting the classification problem, logistic regression is commonly adopted to yield a fitted model and interpret the relationship between independent variables and binary outcomes. By computing the conditional mean utilizing sigmoid function, the probability of outcome variable is obtained. The second model we used is naive Bayes. Naive Bayes is one of the basic machine learning models used for classification to compute the probability that a new data sample belongs to a particular class. Naive Bayes approach has the advantage especially with medical data because all the available information is used to explain the decision. Classification is based on the Bayes theorem. The third model we used is decision tree, which is a supervised learning model approach based on trees that is used for classification problems. It takes an input X and maps it to a discrete label Y. A decision tree considers a lot of features and allows a sequence of splits based on these features. In this approach, we find a decision stump with the best rule, and the data gets split into two smaller subsets. This provides us a good decision tree to use for our prediction task. In this visualization, we can see that the feature considered was systolic blood pressure with a sample of 49,000, and this gets split into two smaller subsamples. The darker color represents that more samples were used in the vertex, and lighter color represents that a smaller sample was considered. The root node of the tree is white because the two samples are equal. The fourth model we used is random forest, which is an ensemble learning algorithm used for classification and regression tasks. A set of decision trees are selected randomly by the random forest classifier from subsamples of the given training set. A voting method is performed on this set of decision trees where the votes are aggregated and a final class is selected. Random forest performs slightly better when compared to decision trees because aggregating the decision trees reduces the noise.
So this is the deep learning part of the machine learning project. I've used the neural networks as the IPYNV file, and I've used the same CSV file as all the other IPYNV files. So we're using the initial setup. We're importing functions like NumPy, Pandas, Keras, Matplotlib, and OS. We're using TensorFlow as the backend. Next, we're loading the data. We're just reading the CSV file into the data frame and using the new cardio train, the CSV file, which I just showed. Next, we're just printing the head and then deleting the ID column since it's not necessary for the prediction. The df dot shape shows the 70,000. These are the 70,000 values, and 13 is the number of parameters that are there. So we deleted the ID column. As you can see in this one, the ID column is there, and in the next one, the ID column isn't there. Next, we are converting the age in days to years. We're just using the lambda map function. We are mapping x to x by 365, which is basically converting days to years. Next, we're checking for null values, which is coming to false, which means none of the values are null. Next, we are checking the distribution. We're using histogram, and we've plotted it. All the parameters are there except for ID, since we've already deleted it. As you can see in the CSV file, all the age, gender, height, till cardio, all are there except for the ID, since we've already deleted it. And next, we've used data values range visualization. We've plotted all the parameters. We've just used a different kind of visualization, and we've combined all of these together. Next, we're dropping the cardio parameter and we're creating a model. This is the sequential model. We've used ReLU and sigmoid functions to create the model. And next, we're compiling the model. We're using a binary cross entropy loss and Adam optimizer. And the metrics we're setting as accuracy. Then we're using the Keras and Tensor board together to compile the function. Next, we're going to the fit, which is we're using history to fit the parameters x, y, and we are splitting the parameters, the test and train, 80-20 ratio, which is the recommended ratio, and the epochs we are setting as 100. The batch size is 16. Generally, we use 8, 16, or 32, but in this case, I've used 16. So we are training on 56,000 samples and validating on 14,000 samples. As you can see, the loss, accuracy, value loss, and value accuracy, these are the parameters that are being printed, and we're noticing the time that it's taking to go through each iteration. As you can see, the loss is gradually decreasing. It's not decreasing, it's overall decreasing. It's fluctuating a bit, but overall you can see it is decreasing. Similarly, the accuracy, it's increasing gradually. It's fluctuating similarly like the loss, but it's increasing gradually. And we've done it for 100 iterations. Uh, then we are evaluating using the scores, and we're evaluating the model x and y. We're using model.metrics name. Metrics name we had set to accuracy previously, and 70,000 by 70,000 it has come. The accuracy has come to 72.83%. Next, we're predicting the model. It's come in the form of array, and we are comparing the validation and training results. We are printing the history keys, which you can see previously. Loss, accuracy, value loss, and value accuracy, the same that we had used. That's what we've used here. Next, we are summarizing the history for accuracy. We've plotted model accuracy versus epoch. Since we've done it for 100 epoch cycles, so the epoch values are going till 100, and our accuracy has come to somewhere around 73%. So it's still 0.73. And this is the blue represents strain and the orange represents test. So this is the model accuracy. Next is the loss. Similar to the accuracy one, it's loss versus epoch. You can see 100.85. And next we're printing the arrays, the true and the model predicting the input prediction. That is what we've printed.
Here is our code. In the logistic regression, we are setting the recursive feature elimination with the cross-validation to choose the optimal number of features for this model. When we got the graph, which is showing the percent of correct classification depending on the number of features that logistic regression have used. Like we saw in the graph, the line reached the highest point when the model has the A feature. Based on the result we got, we only use those features choosing by the feature ranking in the logistic regression. Then we got an accuracy like 72%. Here is the naive-Bayes model. We use the K-best feature selection method to choose what feature we will use. Like we explained before, these 7 features are important features for training the model according to chi-square, which tell us how important this feature is. We trained the model, and then we got accuracy is 59%, which is pretty low comparing the logistic regression. Now here is the decision tree part. First, we made a definition to see the graphic result of the tree model. Then we set up the first tree model with the max step 3 and then trained it. When we see the result of this first tree model with the image, we can take a look each node more closely. Then we can see the rules for classification and Gini entropy, which tell us how much this node carry the information. And this model has accuracy like 72%. However, we want to get more better accuracy for the classification. We need to tune the depth parameter using the grid search cross-validation. Here is the grid search cross-validation result. For each iteration, it has the test score on each depth, so take a mean of those score depending on the depth, and we can find out that depth 6 is the optimal depth for the model. So this part calculate the train accuracy with the first model and the optimal model, and it has the improve around 1.4%. Here is a random forest. Like a decision tree, we trained many times to find the optimal parameter for random forest to use the grid search cross-validation. And comparing each combination and parameter, then when we train the model with the combination. In this way, we got slightly better accuracy than the decision tree model, which is 73.